Hi everyone, welcome to my YouTube channel. My name is Anup Singh. You are watching AeroTech Advance YouTube channel. So guys, in today video we are going to discuss very important chapter, that is Basic Aerodynamics of 2D wing. So we already done few of the topics in on previous video, that we are already covered the topics like geometry parameters of 2D wing, that is airfoil. So we are already discuss all the parameter related to airfoil geometry. Only few important geometrical parameter is left that we are going to discuss in today video. So guys, let's start this lecture. Today is the second lecture of this chapter, that is Basic Aerodynamics of 2D wing. So let's start. So I am going to move the slide up to what we are done. The last slide, yes. So today we are going to see the airfoil nomenclature. So in nomenclature guys, in the real world there are so many airfoils are available and the numbers of family of airfoils are available. So with the help of this I am going to explain you about the very famous family of airfoil, that is a NACA airfoil. In NACA airfoil we are learning the varieties of NACA airfoil series, like 4-digit NACA airfoil, 5-digit NACA airfoil, 6-digit NACA airfoil that we are using in the aircraft wing. So let's see what is that. So I am going to zoom in. So guys, see here the first point, the geometry of many airfoil section is uniquely defined by the NACA designation for the airfoil. Second is there are varieties of NACA airfoil classifications available, including NACA 4-digit, NACA 5-digit and NACA 6-digit wing sections. For example, I am going to take the example, consider the NACA 4-digit wing section. So that is NACA XYZZ. So try to understand how we are going to utilize this method of NACA series in order to understand the geometrical parameter of the airfoil section of particular wing. So the first integer or first digit x indicate the maximum value of the mean camber line in the percentage of the chord. Understand, that is very important, in the percentage of the chord. The first digit indicate the maximum value of mean camber line, means you can say maximum camber. Understand, the first digit indicate x indicate maximum value of camber. The second digit or second integer y indicate the distance from the leading edge to the maximum camber location, but in the 10th of chord, means divide by 10. Understand, means the second digit indicate the location of maximum camber. The first digit indicate the maximum camber in the percentage of chord, but second digit indicate the location of the maximum camber from the leading edge in the 10th of the chord. So this is very important point. Let's see the last two digit. The last two digit here, if you see the last two digit ZZ indicate the maximum section thickness in the percentage of the chord, means the last two digit indicate the maximum thickness in the percentage of the chord. Understand, here example I have given, but with I am going to first take the example, very simple example, then we are going to see the NACA 0012 what is that and NACA 4112. So 1 minute. Yes, so see this guys in this slide, so you guys are understand, everyone is aware that is first digit. What is first digit? First digit specify maximum camber in the percentage of chord. Second digit indicate the position or location of the maximum camber, but in the 10th of chord. The last two digit indicate that maximum thickness in the percentage of chord. So here for example, suppose I have given NACA 2415. So what is that? My question is that what is the first digit? The 2 is the first digit, but what is it indicate? What it signify? So it signify that 2 percentage means 0.02. 0.002 0.002C, that is my maximum camber. What is second indicate? Second indicate 0.04, that is in the 10th of chord, 0.04C, that is the location of the maximum camber. What is the last two digit? That is two digit indicate this, indicate maximum thickness, that is point in the percentage of chord, so 0.15C, that is my maximum thickness. Or you can take in the percentage also, 15% of chord. Always write with respect to C, because C is the chord length. And in airfoil, first we know the what is the chord length. Chord length is already given, 1 centimeter, 1 meter, 10 meter, whatever. But we don't know what is the maximum camber, what is the maximum thickness, what is the location of the maximum camber. We don't know this, but we know the chord length. Understand? So chord length is we already know. That's the reason we are always specifying all the parameter in the terms of chord. So I hope so you guys are understand about the NACA 4 digit. We are going to see about the NACA 5 digit. So this one is the NACA 5 digit. The NACA 5 digit series use the same thickness form as the NACA 4 digit series, but the mean camber line is defined differently, and naming the convection is bit more complex. Not more complex, small, little complex. Okay, so try to understand that NACA 5 digit is given. So try to understand the first digit. The first digit indicate what? Indicate design coefficient of lift, that is a lift in the 10th of chord. But how I am going to get? The first digit is going to multiply by 3 by 2. Suppose x is my first digit, so I am going to multiply by 3 by 2 and I am going to divide by 10th of chord. Divide by 10. C. So with the help of this I can get my design CL. Understand? In the 10th. Second, the next two digit is divided by 2. When divide by 2, it's give the position of the maximum camber in the 10th of the chord. The last two digit again indicate the maximum thickness in the percentage of chord. Means it's similar like a 4 digit series. Only differences between the 4 digit and 5 digit is the 5 digit series, NACA series, giving the direct value of coefficient of lift. Direct value of coefficient of lift. But it is not going to give by the 4 digit NACA series. We are going to use the formula and determine the coefficient of lift. But 5 digit is very important, is giving the direct CL value. Okay, so let's see example, that is NACA 23012. NACA 23012 has the maximum thickness 12%. Obviously the last two digit indicate the location of the indicate the maximum thickness in the percentage of chord. So 12% C. What is my design lift coefficient? Design coefficient, lift coefficient is 0.3, means I am going to multiply by 3 by 2. I am going to multiply by 3 by 2 and divide by 10. So it's give the coefficient of lift. And what is the maximum camber? Location of the maximum camber is the second two digit 30 divided by 2, that is 15, and divide by 100, that is a 10th of chord. Okay, divide by 10th of chord, so I got 15% from the leading edge. So guys, that is very important. So this is the way to signifies the airfoil geometry, and I hope so you guys are understand the NACA 5 digit series. So now we are going to see the next topic. The next topic is about where the important geometrical parameter of the airfoil that affects the aerodynamic property of the 2D wing. That what we are left on the previous lecture. So today we are going to see each and every parameter in little bit detail. Not much detail, but in little bit detail, because many of the students are taking the project to design his own airfoil and do the analysis. So this is a very important. What is the design constraint with respect to the parameter? So let's see the leading edge radius and chord line. So leading edge radius The chord line is defined as the straight line connecting the leading edge and trailing edge. Very simple definition that you guys already know. The leading edge of an airfoil used in the subsonic application is rounded. But if you see in the supersonic, the leading edge is not round, leading edge is sharp because of shock wave. Shock wave is generating. That's the reason we are putting sharp leading edge like a wedge shape with a radius that is the order of 1% of the chord length. That is a typical value. Your leading edge radius always within the 1% of chord length. Understand? So this is important. Second, the leading edge radius is the radius of a circle centered on a line tangent to the leading edge camber and connecting the tangency point on the upper surface and lower surface with the leading edge. Then the whole airfoil is going to generate it. What I told you on the previous video. Upper surface and lower surface equation, mathematical equation is available. But what about the leading edge? So you required to draw the circle with a described radius to do the tangency to the upper surface and lower surface that give the smooth aerodynamic shape and generation of the airfoil. The next point is about center of the leading edge radius is located so that the cambered section projected slightly forward to the, this is a design point of view. If you are designing, so this fourth point is very important. Then last point is about the magnitude of the leading edge radius has significant effect on the stall characteristics of the airfoil section, especially if the leading edge radius is too small. It is not following the 1%, so too small. So what happens? There is a tendency of flow separation, that is called stall characteristics having more. So that is disadvantages, guys. In the stall condition, what happens? The coefficient of lift is decreasing suddenly. That is not our favorable condition. The stall characteristics is an unfavorable condition. That is, if the wing or airfoil is going to stall, it means that the lift is suddenly decreases and drag is suddenly increases. That is an unfavorable condition, and that is very important to know everyone. Otherwise, so that is we are going to discuss at the end of this chapter, don't worry. So this is about the leading edge radius and chord line. So I hope so you guys are understand this one. Now next is about mean camber line. So guys, the mean camber line is what? The mean camber line, the locus of the point midway between the upper surface and lower surface, a measure perpendicular to the chord line defined as the mean camber line. This one, if you see the dotted line in this figure, so you can easily understand what is the mean camber line. This is a dotted line, that is a mean camber line. The shape of the mean camber line is very important to determining the aerodynamic characteristics, because the mean camber line deciding the camber is the property of the lift. This area, whatever I am dashing, that is a camber. That is very important for lift generation, property of the airfoil. If the camber is more, means lift generation is more. Cambered airfoil in the subsonic generate the lift at zero angle of attack because it's already having the camber. But if you see in the symmetrical airfoil, camber is zero because camber line and chord line both are coincide with each other. So camber has the benefit on the maximum value of the lift coefficient, that is CL max. So if the maximum lift coefficient is high, so stall speed will be low and other factors being the same, that we are going to discuss in the stall characteristics. So don't worry, stall characteristics, in that part I am going to first talk you about boundary flow separation. Flow separation is very important, and what's the reason flow separation is happen in the case of stall characteristics, and how the stall characteristics is and stall condition is arises in the case of aircraft wing. That is also we are going to discuss. So guys, here we have discussed so many things like angle of attack and camber, that is very important to know. So guys, try to understand about that parameter like angle of attack. So guys, angle of attack is the angle between the chord line and the relative wind direction, that is called chord line. This is the relative wind direction and this is the chord line. So this is called angle of attack alpha. Alpha is the notation of angle of attack. If the greater angle of attack means more lift. alpha is high, it means a CL is also high, coefficient of lift is also high. So this is about the definition of angle of attack and airfoil shape. What I have discussed earlier on the previous video, there is a two shape of the airfoil available in the market, that is symmetrical and asymmetrical. Asymmetrical means cambered airfoil. So in symmetrical there is no lift because there is no camber at zero angle of attack, but in cambered airfoil lift is generated at zero angle of attack because there is a camber. Camber is already there, and camber is the property of the airfoil. So I hope so you guys are understand this airfoil shape, that is already we are discussed. So guys, here we are going to stop our, this is second lecture of the chapter Basic Aerodynamics of 2D Wing. In next lecture we are going to see the remaining topic of geometrical parameter of the airfoil, and also we are going to discuss very important points related to boundary layer flow separation and stall characteristics. So guys, if you guys have any doubt related to in today lecture topic, you can ask me in the comment box, question in the comment box, otherwise you can follow my Instagram and ask in the chat box. Okay, so thank you everyone for watching my videos. Thank you.